Welcome to today's Explainer. We're jumping right into one of the most fascinating topics in the physical world. Now, if you're a student completely new to physics, don't worry, we are going to use some really simple everyday analogies to make these concepts a breeze. Physics is literally just the study of the invisible rules governing our world, the hidden machinery behind everything. Today, we're stripping away the dense jargon and looking at exactly how fluids, like air and water, behave. Trust me, you're going to walk away seeing the world completely differently. Okay, let's dive into this. Consider this little mystery. On the surface, a heavy metal submarine exploring the crushing depths of the ocean, and a sleek airplane soaring through thin clouds. They seem like total opposites, right? One navigates water, the other air. But here's the thing. To a physicist, water and air are exactly the same thing. They're both fluids. And both of these incredible machines rely entirely on mastering two distinct types of invisible fluid pressure to survive. So let's crack the code on what these pressures actually are. Section 1. Invisible force, static pressure. To really grasp what static pressure is at a molecular level, I want you to picture this. Imagine you're standing perfectly still in the middle of a packed, energetic room. The people around you aren't moving in any specific direction, they're just milling about randomly, constantly bumping into you. Front, back, left, right, just constant bumping. In the physics world, those people are fluid molecules in a state of constant random thermal motion. Even when a fluid looks completely still to us, microscopically, its molecules are frantically bouncing off each other and off whatever is submerged in them. Which brings us to the formal definition. When all those microscopic molecular bumps happen trillions of times a second against the surface, they add up to a very real macroscopic force. This is what we call static pressure. It's the actual thermodynamic pressure of a fluid at rest. The absolute key takeaway here is that because this molecular bouncing is totally random, the pressure pushes equally in all directions. It's an omnidirectional force. If you're standing in that fluid, you're being squeezed evenly from every single side. Now, let's look at the math behind this crowded room. And hey, please don't let the formula intimidate you. It's actually beautifully simple when you break it down. Static pressure, or PS, is calculated by multiplying just three things. You've got rho, which is the density of the fluid, basically how tightly packed our crowd is. Next is G, which is gravity pulling that crowd downward. And finally, H, the height or depth of the fluid column above you. That's it. It literally just means the deeper you go into a heavy fluid, the more weight is pressing down, and the harder those molecules are forced to bump into you. To put that into perspective, take a look at this massive number, 101.3 kilopascals. That is the static pressure of the Earth's atmosphere resting on your shoulders right now at sea level. Because we live at the bottom of an ocean of air, the weight of the atmosphere is constantly pressing inward on us. We casually walk around in it every single day without noticing, mostly because our bodies have evolved to push back with the exact same pressure. But make no mistake, that invisible omnidirectional force is absolutely immense. Section 2. Energy of movement, dynamic pressure. Let's go back to our analogy. The random milling about in that crowded room has suddenly changed. Imagine a fire alarm goes off, and the entire crowd suddenly starts running together in a stampede toward a single exit. If you're standing in front of that door, you're no longer getting bumped randomly from all sides. No, you're getting slammed with a massive directional force from the running crowd. This ordered directional movement of mass carries incredible kinetic energy. Think of the powerful push of a gale force wind against your chest, or the massive kickback a firefighter feels when a high-velocity stream of water shoots out of a hose.
And that brings us to dynamic pressure. By definition, this is the additional pressure created specifically by the kinetic energy of a fluid in motion. Unlike static pressure, which squeezes you from everywhere, dynamic pressure is highly directional. It only acts parallel to the direction of the fluid's flow. And here's a fascinating quirk about it. You actually can't feel dynamic pressure directly unless you force that moving fluid to come to a complete stop against an object. When the fluid hits an obstacle and halts, its kinetic energy instantly converts into a crushing physical force.
If we look at the math of motion, it's going to look very familiar. Dynamic pressure is calculated as 1/2 times the fluid density times the velocity squared. You probably recognize this directly from the classic kinetic energy equation from high school. 1/2 mass times velocity squared. Notice that little exponent on the v. Because velocity is squared, an increase in the fluid's speed doesn't just bump the pressure up a little bit, it increases it exponentially. If the wind blows twice as fast, the dynamic pressure pushing against you is 4 times as strong. Section 3. Core differences of the two. Now, what's really interesting about this side-by-side comparison is how perfectly it contrasts these two distinct behaviors of nature. Look at the source row. Static pressure is born from thermal energy, that random, chaotic molecular motion. Dynamic pressure comes from kinetic energy, ordered bulk movement. Static pressure exists whether the fluid is still or moving, pushing everywhere omnidirectionally. But dynamic pressure, it only exists when the fluid has a velocity greater than zero and it pushes in one specific direction. Understanding these contrasts is absolutely crucial to unlocking how vehicles master the skies and seas.
Section 4. Physics budget, Bernoulli's principle. To really nail down how these two interact, we're going to use one of my absolute favorite analogies. Imagine you have a fixed allowance of pocket money, let's say $10. This $10 represents the total energy in a closed fluid system. You can spend your money on exactly two things: moving really fast, which is your dynamic pressure, or pushing outward, which is your static pressure. If you decide to spend $8 on moving incredibly fast, you only have $2 left over to push outward. If you slow down and only spend $2 on speed, you suddenly have $8 to push outward. The fluid has a strict budget.
This budget is formally known as Bernoulli's equation. It tells us that total pressure, also known as stagnation pressure, equals static pressure plus dynamic pressure. So the crucial point is this. In a closed, frictionless system, the total pressure remains completely constant. The two pressures constantly trade places to maintain that balance. If the velocity of a fluid increases, driving the dynamic pressure up, the static pressure absolutely must drop to balance the budget. This simple trade-off is the underlying secret to how airplane wings actually generate lift.
Section 5. How airplanes measure speed.
Let's bring everything we've learned together and solve the mystery we introduced at the very beginning. How exactly do airplanes use these invisible pressures? Well, this brilliantly illustrates the real-world genius of applying physics. Enter the Pitot-Static tube. It's a device you'll find on the nose or wing of almost every single airplane in the world. See, up in the sky, there are no road signs or mile markers to tell a pilot how fast they're going. They're moving through an invisible, featureless fluid. So aeronautical engineers designed this simple mechanical instrument to physically capture the math we just learned, acting as the airplane speedometer. Let's walk through the logic step by step. Step 1. The pitot tube is a hollow pipe facing directly into the wind. It catches the fast-moving air and brings it to a dead stop inside the tube, capturing both the static squeeze and the dynamic kinetic energy. That gives us the total pressure. Step 2, along the side of the aircraft are tiny holes called static ports. Because they sit parallel to the airflow, the wind rushes right past them without stopping, allowing them to measure pure, unadulterated static pressure. Finally, step 3, the flight computer simply takes Bernoulli's budget and does the math. It subtracts the static pressure from the total pressure. The remainder is purely the dynamic pressure. And since dynamic pressure is directly tied to velocity, the airplane now knows exactly how fast it's flying.
It is absolutely incredible, isn't it? Just a simple understanding of molecular motion and basic algebra allows a 400-ton metal machine to navigate safely through the invisible sky. Physics isn't just numbers on a page, it's the language of reality. So I want to leave you with this thought to carry into your day. The next time you're riding a bicycle down a steep hill, or you stick your hand out the window of a moving car, or you just feel a strong gust of wind against your face, ask yourself, which invisible pressure is pushing against you right now? And what happens to that energy when the wind finally stops? Keep observing, keep questioning, and I'll catch you in the next explainer.